Okay, so I will talk today about forward completeness for time delay systems and a bit also for systems without time delay. So I have to say that this is joint work with my colleague, Jose Luis Mancilla-Aguilar, who is here in the audience. Okay, so this talk was motivated by two previous seminar presentations in this seminar series, one from Antoine Cheyet on the 19th of July, where he presented ISS for delay systems and presented some open questions that spiked our interest, and also by the talk by Andri on robust forward completeness as a bridge between well-posedness and stability. So after these talks, and we started thinking about some open questions that were presented, and this is what I will present today, which is, I will also be mentioning these three publications that are on the screen, one by Andri and Fabian Wirth, one from Jason Karaphilis and co-authors, and another one from Antoine and Jason and co-authors. Okay, so let's begin with an ODE system. So the usual assumptions that we have for an ODE systems in order to have unique solutions are, of course, for ODE systems, we have the state spaces Rn, or a subset. The set of inputs that is considered is those of functions that are defined from 0 on and are measurable and locally essentially bounded. And the usual assumption is that the function f defining the ODE is continuous in all variables. It's continuous as a multivariable function, and that it's Lipschitz with respect to x on bounded sets for x and for u. That is what is written on the screen. I will use the notation B sub r superscript n for the closed ball of radius r in Rn. So these are standard usual assumptions that cause the usual properties of local existence and uniqueness of solutions in Kara-Theodori sense. And the boundedness implies continuation property, which essentially means that if the solution is bounded, it cannot cease to exist. Or if it ceases to exist, it must become unbounded in a finite time. Okay, so let's consider as well a subset of inputs, which is those of the continuous inputs. So I will use U for the set of measurable and locally essentially bounded inputs, and U sub C as the set of continuous inputs. And under the previous usual assumptions, we know that we have a unique solution that I will name phi, corresponding to an initial condition x naught and an input U. And the solution will have a maximum time of definition T sub phi. So with this notation, we define forward completeness when every maximally defined solution exists for all times. And this means for every initial condition in Rn and for every measurable and locally essentially bounded input. I will define another related property, which is forward completeness for continuous inputs, which is the same, but only considering the subset of inputs that are continuous. So it is clear that forward completeness for continuous inputs is weaker than forward completeness, right? It's a weaker property because solutions have to exist for all times, but only for a subset of all possible inputs. And we have a stronger property, which is robust forward completeness from an input, or equivalently boundedness of reachability sets, which is the fact that the system is forward complete, but in addition, we have a uniform bound for solutions originating from bounded initial conditions with bounded inputs. And I stress that here the input can be any measurable and locally essentially bounded function, right? Over a compact time interval, right? So it is clear from the definitions that robust forward completeness is stronger than forward completeness, which in turn is stronger than forward completeness for continuous inputs. Okay, so what we know from some time already, this paper by Lin, Sontag, and Wang showed that actually forward completeness and robust forward completeness in this sense are equivalent properties for ODE systems. Actually, the result given by Lin, Sontag, and Wang does not can be used to show this equivalence with these definitions that I wrote here. Okay, so we know that robust forward completeness is equivalent to forward completeness. What happens with forward completeness for measurable inputs and forward completeness for only continuous inputs? And it turns out, this is not so well known, I may say, that forward completeness for continuous inputs is not equivalent to forward completeness. So FCC does not imply forward completeness. And we will see that with an example from switch systems. So consider this system without delay. It is an ODE system, which is a two-dimensional state and has an input, or U, which is a scalar value, a real valued input. So this system has a scalar factor here, which is 1 plus the Euclidean norm of x squared times a matrix times the state. So it's a time-varying matrix here times the state. And this matrix, A of phi, since phi is a saturated identity, let's say, it saturates below at 0, above at 1. So this A of phi is just a convex combination of two matrices, A0 and A1. Both A0 and A1 are Hurwitz stable matrices. Okay, so by choosing the value of the input, I can select which convex combination of A0 and A1 I want to set here as the matrix in the equations. Okay, so note that, as I said, this phi is a saturated identity, and that for any argument of the function A of 1 is equal to A1, and A of 0 is equal to A0. And with these definitions, we see that this function G here, sorry, let's see if I can. This function G here is locally Lipschitz. So it's not just Lipschitz with respect to X, it's locally Lipschitz in all variables. Okay, so how does this ODE2 system work? And to have an idea of how this could behave, let's consider now the simplified system, which is a switch system, where it is the matrix A0 or A1 multiplied by X here. So sigma is the switching function. Its values can only be 0 or 1. So I'm selecting only the matrix A0 or A1 at every time instant. And I see here that if the matrix is A1, I have the phase portrait here on the left, which is like short and wide spirals that rotate in the clockwise direction. And if the matrix is A naught, I get the tall and thin spirals that also rotate on the clockwise direction. Okay, so you see that this is a standard example of a switch system with stable subsystems, but I can make it switch in such a way that I can make it unstable, right? So if I select A1 in the first and third quadrants, and I select A0 in the second and fourth quadrants, I will have an unstable behavior, and that's what I'm showing here, right? So if we look at the phase portrait of this with this switching function defined, as I said, I see that I get A1 here, A0 here, A1, and so on, and I make it unstable by switching. And here I see the time evolution of X1 and X2, and I see that the switches are uniformly spaced because of the way the system behaves, right? And it's unstable, but forward complete, because it becomes unbounded only as time tends to infinity. Okay, so what happens if we now add the scalar factor that the previous system had? So we add this scalar factor here, and it turns out that the phase portrait doesn't change because it's just the scalar factor scales the derivative, right? But the time evolution is compressed into a finite time interval. So this system now, with this scalar factor added here, has a finite escape time, right? And this example is taken from one of Jose Luis's papers, co-authored with Eduardo Sontag. And this was actually key to showing some of the results that I will be showing to you in some minutes. Okay, so we see that the difference between the previous and this one is that the time evolution changes so that it becomes not forward complete, right? The solution ceases to exist. And if we look at the switching function that generates this behavior, it's something like this. It switches here, here, and here, the switching times with a dashed line. And we see that it has an accumulation point of discontinuities toward the finite escape time of the solution. And from that time on, we can extend this function by setting, say, constant zero value so that it becomes a measurable and bounded function defined from 0 to infinity, right? So let's keep in mind that I will call sigma this function that looks like this up to the finite escape time, and then it's extended with a 0 value to infinity. Okay, so what about the original ODE2 system, right? Is it forward complete? Well, it's not, because if I select the input u as the function sigma that I mentioned in the previous slide, right? It turns out that all phi of u will be equal to, so this whole a of phi of u will be equal to a0 or a1, and I will make it diverge in a finite time. So I can say that this system is not forward complete for measurable and bounded inputs. But what happens for continuous inputs? Is this system forward complete for continuous inputs? And so it turns out that it is. So we have an example of a system that is forward complete for continuous inputs, but not for measurable and locally essentially bounded inputs. And to see why this is forward complete for continuous input, we have to keep in mind that continuous input has to be defined from 0 on, right? So what I call my set of u sub c of continuous inputs are continuous in the time interval from 0 to infinity. Okay, so with that in mind, the main idea for showing that this system is forward complete for continuous inputs is that, well, as I said, the function phi is a saturation of the identity. any convex combination of A0 and A1 is Hurwitz because of the precise form of A0 and A1. And if that happens, then for every convex combination, I can have a quadratic Lyapunov function, right, defined by this symmetric and positive definite matrix P sub lambda, where lambda identifies which convex combination I'm taking. And for a contradiction, consider an initial condition, a continuous input defined from 0 to infinity, and suppose that the solution has a finite escape time, right? Then it could happen, it will happen that in a neighborhood of the finite escape time, the system admits a quadratic Lyapunov function, right? Given by the convex combination that is identified by this phi of u evaluated at the escape time. And if the system admits a quadratic Lyapunov function in a neighborhood of that time, no matter how small the neighborhood, then it cannot diverge there at T phi. So it's a contradiction. So this system has to be forward complete for continuous inputs. Okay, so we have now shown that forward completeness for continuous input does not imply forward completeness. So we have the complete picture for ODE systems. What about time delay systems? Okay, so we have to stress that the true state of a time delay system is not just a vector in Rn, but the whole piece, a segment of a function from T to Rn. So for example, that's what we will call x sub t, which is the evolution history of the state at time t, which is the true state of a time delay system, which is the segment of evolution of x from time t backwards, tau time instants, time units, where tau is the maximum delay involved in the dynamics, right? So we use x sub t now to denote that interval of the function. We will use the norm as the standard supremum norm, and we will consider, okay, I will say that in a minute, but you see that if I want the value of x at t is the same as x of t evaluated at 0 by the definition, and my initial condition now will be a segment piece of a function, right, x of 0, which is the x defined from 0 to minus tau. Okay, so now I have the retarded functional differential equation, usually written in this form, where now f maps a segment of a function times a vector in Rn into into Rn, and these pieces or segments of functions that I put here will be defined from minus tau to 0 into Rn and will be continuous. So we'll use C for this set of continuous functions, right? And I will use this notation for the closed ball of radius r in this space or set of continuous functions, taking the supremum norm. So the standing assumption that we will have here, which is a bit stronger than the analogous one for ODE system, is that this f is Lipschitz on bounded sets. So it's Lipschitz in both variables, right? Simultaneously, not just in the state part. Okay, so with this assumption, we have unique solutions defined up to some maximum time, and the boundedness implies continuation property. And this is a key observation here, that a solution to this retarded functional differential equation is absolutely continuous only from 0 on, but not before. From 0 to minus tau, it's just continuous, but not, it's given by the initial condition, and just continuous. But it's absolutely continuous from 0 on. So it behaves much, it's much nicer from 0 on that it can be between minus tau and 0. Okay, so again, recall the notation for all the measurable and locally essentially bounded inputs and the continuous inputs, and we have the analogous definitions for forward completeness for continuous inputs, and robust forward completeness from the input U or boundedness of the reachability sets, where now the initial conditions are pieces of a function with a supremum norm bounded by R, and the inputs are all measurable locally essentially bounded inputs, again with supremum norm bounded by R, and time in a compact time interval, I have a uniform bound for the solution, and that's the boundedness of the reachability sets or the robust forward completeness property. So we already know that forward completeness for continuous input does not imply forward completeness for ODE systems, which are a special case, we could say, of this more general type of systems. So what happens with the other implication? We knew that RFC is equivalent to FC for ODE system, but what happens for time delay systems? Okay, and this is where we took, let's say, motivation from Andres and Antoine's previous talks, right? So we know that time delay systems are infinite dimensional. And Andre and Fabian showed that in general, forward completeness does not imply the boundedness of reachability sets in an infinite dimensional system. But Antoine and Jason conjectured that they could still be equivalent for the special case of time delay systems because the counterexamples in the paper by Andre and Fabian are not time delay systems. And also Jason and co-authors in this paper say that this is a central question that deserves deeper investigation. So we were very motivated to look into this issue. And this is spoiler alert, they actually are not equivalent for time delay systems. And that's what I will try to show in the remainder of this talk. Okay. So let's recall the previous ODE system and make it part of a time delay system. In what sense? In this sense. Now, the input U here will be replaced by a delayed version of this other variable that is part of the newly defined system here, which behaves as a decaying exponential from 0 on, but between 0 and minus tau is any continuous function, right? Because the initial condition for a time delay system can be any continuous function. So we know that the solution for the Z part of the system is the initial condition between minus tau and 0, or a decaying exponential, and the equation that governs the X part of the solution is given by the initial condition of Z from 0 to tau, right? So it's given by the initial condition for X between minus tau and 0. I'm not writing that. That's the solution X, but the dynamics, the derivative of X is given by the initial condition for Z as an input here between 0 and tau, and by the decaying exponential with a delay from tau on, right? So we see that we have this time delay 2 system that is the same one I'm presenting, that is whose Z part of the solution exists already for all times, we know that. And by the fact that the dynamics of X is governed by, say, this delayed Z, which is continuous, then the dynamics of X or the X part of the solution corresponds to the previous ODE system under a continuous input, which we know exists for all times. So this system, TD2, the time delay system, it is indeed forward complete. But what happens with robust forward completeness? Is it or not robustly forward complete? Let's see. So recall this switching signal sigma that I showed and extended into a measurable signal with a zero value, constant zero value, so that it is defined from 0 to infinity. Set tau greater than the finite escape time here, right? Select the sequence of initial conditions for the Z part of the solution. These are segments of continuous functions, so that they are bounded between 0 and 1, and so that they approach the switching signal, this one, extended, as I mentioned, for almost all time instants between minus tau and 0. So they trying to approximate this continuous function with a sequence of continuous functions that are bounded between 0 and 1 and converge pointwise almost everywhere to this sigma. And set the initial condition for the X part of the solution constantly equal to the same initial condition that I showed in the previous simulations, where I showed the phase portrait and the time evolution. The initial condition was this one. So I set the same one. And now consider this sequence of initial conditions for the whole system, where the only thing that changes with the index k of the sequence is the Z part of the solution, but the x0 is the same, and is this one constant for every k. So we see that in the supremum norm, we have a bounded sequence of initial conditions, and it is uniformly bounded for all k. Right, so now I'm sorry for that the notation gets a bit clumsy here, but I'll try to explain as simple as possible. So consider now the solutions of the system, but between 0 and tau. So the solution, the complete solution, has a Z part and an X part. And I will be considering the solutions for the different initial conditions in the sequence. So the Z part, the derivative is just minus the Z part of the solution, and we know that the solution from 0 on is a decaying exponential, right? And the X part of the solution, right, has this derivative where, since I'm considering only from 0 to tau, then this part that drives the X part of the solution corresponds to the initial condition for Z, right, which was taken as the sequence that approximates the sigma, right, the switching signal, right? So now for a contradiction, if the time delay 2 system were robustly forward complete, it should happen that the solutions will be uniformly bounded for initial conditions that are uniformly bounded and in a compact time interval, right? And let's call that bound M. This is a consequence of our contradiction assumption that the system is RFC, right? Now, if this holds, that the X part of the solution is bounded, uniformly bounded for any initial condition here, then we also have a uniform bound for G, for this right-hand side here, right? And by the Lipschitz assumption, or the Lipschitz property of G, this is also bounded uniformly, taking any initial condition in the sequence here, right? So if I consider the continue with the reasoning, then I have that the solutions, and we have to interpret this sub tau means that I'm taking the segment of the solution of the X part of the solution from 0 to tau, and corresponding to each of the initial conditions in the sequence. Each of these is a function defined from minus tau to 0. As I mentioned, what happens when I put a subscript here. So this sequence of functions is equibounded and equicontinuous. So by Arcelà-Ascoli theorem, it has to have a uniformly convergent subsequence. So let's call this subsequence by case of L. So the set of indices, the sub-indices from K, the case of L, and this subsequence has a limit, a uniformly convergent subsequence, so it's the limit is a continuous function, right? So let's use this information into what we know about the solution. So here I copied what x of tau is, the limit of this subsequence. And if I take the limit here, but now at time t, right, that is that is by this definition here, it has to be x at t. And by using the definition for this, I have that is x0 plus the limit. So it's the limit of x at 0 plus the integral, but the x at 0 is a constant, so I just put the limit on the second term of the summation here. So it's a limit of this integral of the derivative of x, right? And then by the Lebesgue dominated convergence theorem, I can sort of put the limit inside the integral, and then by the this converges uniformly to x, and this converges pointwise almost everywhere to sigma, right? So I see that if my contradiction assumption were true, that the system were robustly forward complete, the solution would have to correspond to the input given by sigma, which we know has a finite escape time before tau, but this holds up to tau. So this is a contradiction. So this system cannot be robustly forward complete. So time delay systems can be forward complete, but not robustly forward complete, even if they don't have inputs, as in this case. And so we have the complete picture that we don't have any of the converse implications here for time delay systems. Okay, so in our effort for proving that this could be so, for getting this counterexample, which is the breakthrough in getting this counterexample, I repeat, was made by José Luis Mancilla-Aguilar, who realized the connection between this and his earlier work. But in our effort to do this, we came up with this, we had to come up with this characterization of forward completeness and robust forward completeness for time delay systems, which is the following. Let's consider now this time delay system, which is a standard time delay system in the sense that it contains a function depending on the current state and delayed versions of the state. Well, what we call the state, the x, which is not the state in the time delay system sense, right? And let's define, based on the time delay system, another system where I replace the delayed states by continuous inputs, which I call V, so that they are different from U. So U is any measurable locally essentially bounded input. V, any of the V's are only continuous inputs. And we have this characterization of forward completeness and robust forward completeness. If this F is locally Lipschitz, then the time delay system is robustly forward complete if and only if the ODE system is forward complete, right? And by forward complete, I mean that also the V's have to be measurable and locally essentially bounded. And the time delay system is only forward complete if and only if the ODE system is forward complete for continuous V and for measurable and locally essentially bounded U. And this is the main, let's say, theoretical result, which is not a counterexample, I mean, in our recent submission here that you can find on arXiv. Okay, but that's not all. So let's say that I covered the intuition part of the talk. Now let's speak about counterintuition. So it turns out that this example is not just showing that forward completeness is not equivalent to robust forward completeness for time delay system. It actually shows much more than that. And we will see what it shows. Okay, so let's consider now retarded functional differential equations with no input, defined by this equation, where the function f naught is Lipschitz unbounded sets and is 0 at 0. So we have an equilibrium at 0. And with this assumption, we have a unique solution that we will call X, that depends on the initial condition and has a maximum time of existence T sub psi. And we say that the system or the zero solution of the system is Lyapunov stable in the usual sense, right? If given a bound for the trajectory, I can find the bound delta for the initial condition so that any trajectory originating with such a bounded initial condition is bounded by the original epsilon bound. I say that it's globally attractive if any trajectory converges to 0 for any initial condition. And this implies that the system is forward complete. I will say that it's uniformly globally attractive, which is stronger than globally attractive, meaning that it's not just globally attractive, but solutions originating in a bounded ball will have a uniform convergence rates, let's say. That's the difference between globally attractive and uniformly globally attractive. And I will say that it's globally asymptotically stable if it's Lyapunov stable and globally attractive. And the strongest of all these properties is the uniformly globally asymptotically stable property, which essentially means that I can bound the solution with a KL function beta, depending on the norm of the initial condition and the elapsed time t. And this I can do for any initial condition and for any future time. So Jason and co-authors in this paper proved that global asymptotic stability, in addition to robust forward completeness, is equivalent to the strongest property, right? So we know that global asymptotic stability, as I said, implies forward completeness, but now we know that forward completeness does not imply robust forward completeness. So what can we say about the equivalence between global asymptotic stability and uniformly globally asymptotic stability? And we can use this same example actually to show that the system, the time delay system that I presented, is Lyapunov stable and uniformly globally attractive, but not uniformly globally asymptotically stable. So this shows that global asymptotic stability, not even in combination with uniform global attractivity, can imply uniform global asymptotic stability in the sense given by the previous definitions. So I consider this to be really counterintuitive, but let's see if I can give you some idea on why this happens in this example. So to prove Lyapunov stability, right, we can choose the initial condition as small as we want so that the trajectories remain within the epsilon bound, right? So if we have a small initial condition for the z part of the solution, we will have a small z for all times from minus tau on, right? And if we have a small z part of the solution, then because phi was a saturated identity, we will have a small phi of z delayed. And if we have a small phi, then A of phi will be continuously close to A naught, which is Hurwitz, right? And then we can have a quadratic Lyapunov function to ensure local, actually exponential stability. So that's the, let's say, the rationale for showing that this time delay system that I gave as an example is Lyapunov stable. What about uniform global attractivity? So I have to give a bound for initial conditions and the final bound for the norm of the state. And now this is a bit different. I have to wait because lambda bar can be as large as one wants. So I have to wait until the z part of the solution decays to some small norm in a time that will depend on lambda bar and epsilon. But in the meantime, I know that the x part of the solution cannot cease to exist because the system is forward complete, right? So I wait for the up to T1, and then I analyze what happens from T1 plus tau on, and I take the same Lyapunov function that I'm mentioning here. I take the same one, and when I analyze what happens with the derivative of this Lyapunov function evaluated at the trajectory, on the trajectories, I get this inequality. The inequality is much, much stronger than this one. I'm just taking a consequence of what the derivative satisfies so that I can prove. But the main idea is that I can converge to epsilon, to within epsilon of the origin in a time that is independent of initial conditions, because that's the squared, what the squared here does. So using a comparison lemma, I actually get that the W of t is bounded by this if time is actually greater than T1 plus tau. And I see that this converges to epsilon in some time that is independent of the initial conditions, but dependent on T1. But T1 is dependent only on the given lambda bar and epsilon. So this is, to me, this is really counterintuitive. So we can have a sequence of bounded initial conditions that causes larger and larger intermediate peaks, but with uniform reachability times to epsilon. So if I took the same sequence of initial conditions that I mentioned in the previous slides, and I looked at the evolution, the corresponding evolution, the state will have an intermediate peak that grows larger and larger and larger up to infinity without ever reaching infinity. That's in a limiting sense, right? And then comes back from infinity also in a finite time to within epsilon. So I consider that really counterintuitive. So coming to the conclusions of the talk, I have considered ODE systems, time delay systems, the time delay system with the delayed states replaced by these V functions, which I call ODEV, and the general retarded functional differential equation. And we've seen that ODE can be forward complete for continuous inputs, but not in general. And I've shown also that the time delay system can be forward complete, but not robustly forward complete. And I have shown also that the forward completeness and robust forward completeness of the time delay system are equivalent to the forward completeness for continuous input V here, or forward completeness of the ODEV. I'm saying this not precisely, just to recall what I mentioned on the talk. And okay, so as you see, our relationship with our characterization of forward completeness and robust forward completeness is for this specific form of time delay system, which I call TD. But what happens for the general? What happens for a system that could be written in this form, but not as TD form? So can we have a similar characterization, or what would the characterization be for robust forward completeness? Okay. This is the end of my talk. Thank you very much. I'm open for questions.